So last time we talked about this idea of equilibrium, the balance point, if you will, between reactants and products as to how far our reaction moves towards one side or the other. But how do I know if my reaction is actually at equilibrium or not? Well, that's where this reaction quotient comes in. Reaction quotient is usually represented by this letter Q, and the formula for Q is just like the formula for our KEQ. Putting products over reactants. The only difference between Q and KEQ is that KEQ is the constant of equilibrium. There is no net change between my reactants and products. Those concentrations are constant. However, Q, I have no idea where my reaction is. It might be at equilibrium, it might not be. I don't know where it is. So a Q calculation will allow me to determine if my reaction is at equilibrium, if Q equals KEQ, or perhaps if my reaction still needs to shift one direction or another in order to reach that equilibrium position. So that's what we're looking for. So here's an example where we would need to use our Q calculation. The problem tells us that nitrogen and oxygen react to form nitrogen monoxide. A lot of times in these equilibrium type problems, they will tell you the reaction. You won't have to necessarily come up with it yourself. So let's see, balance that real quick. And these are all gases. So these are all going to go in my KEQ and thus my Q expression. The problem tells us our KEQ. It tells us that our KEQ has been determined for whatever temperature that we're at to be 1.3 times 10 to the negative fourth. Since I have a number less than 1, that tells me that this reaction tends to hedge more towards my reactant's side. It doesn't go very far towards this product. It tends to stay over here. Because to get a decimal like this, we had to have a higher concentration of my reactants to my products. It tells me that the current concentration of my reactants, I'll go ahead and translate them on down here, are both 0.5 molar, 0.5 molar, and the concentration of my products is 0.004 molar. That seems to support our earlier statement of having more, sorry there, you couldn't see that, having more reactants than products. Whoop, star chart. But I want to know, is my reaction at that equilibrium point from here? Will my concentrations continue to change, or am I at that happy, stable, unchanging point? So we're going to use Q. And again, the only difference between KEQ and Q is the fact that I don't know yet if my reaction is at equilibrium. To be at equilibrium, my Q should equal my KEQ. So let's find out. We're going to do products over reactants just like we do for KEQ. So my products are NO, and since there's a coefficient of a 2 here, this is squared, divided by my nitrogen concentration times my oxygen concentration. So let's see what value I get for my Q. These two down here are multiplied, in case you forgot. So let's see, we have 0.004 squared divided by 0.5 times 0.5, and we get 6.4 times 10 to the negative fifth. Now look at these two numbers. They're not the same. That tells me that no, I am not at equilibrium. My concentrations will not stay constant, and they will in fact change. But let's see if we can figure out which way we need to shift. If I look at my two numbers here, if I look at my Q compared to my K. My Q is smaller than my K. Smaller decimals mean higher concentrations of the stuff on the bottom. We're dividing by bigger numbers. So since this is too small, that means these numbers are too big. If these numbers are too big, my reaction needs to shift further towards my products. I need more of this top number. I need to make this number bigger to get towards my 1.3 times 10 to the negative fourth. That is my equilibrium, my KEQ. So my reaction will continue to shift towards products. We need to make more products in order to get this reaction to equilibrium. So my two reactant concentrations will go down. My product concentration will go up before I hit that unchanging, no net change balance point of equilibrium. Let's see if I can find another example for us to look at. Here's one. So let's say, this is a practice problem off of a sheet that I give my students. We have hydrogen and chlorine gases reacting to form hydrochloric acid in gaseous form. They give us our KEQ and they give us our current concentrations. And they want to know if we are at equilibrium. So here we go. Hydrogen gas is in Brinkelhoff, so that's H2. Chlorine gas, also in Brinkelhoff, H2. Equilibrium reaction is reversible, makes HCl in gaseous form. Since these are all gases, these will all go both in my Q and my KEQ. Let's go ahead and write the KEQ from the problem over here. 0.8. Now this is still less than 1. So this tells me that we do still favor the reactant side of my equation. Because if you remember, our fraction, to have a decimal less than 1, this bottom number, my reactants have to be bigger. But compare this to the problem we just did. We're at something to the negative fifth. This reaction makes a lot more products than our previous one did. I'll go ahead and transfer over the information from our problem so we don't have to keep going back and forth. There we are. So we want to know, is this equation at equilibrium? Are these concentrations going to continue to change, or will they stay constant with my net reaction staying the same? I don't know. Let's find out. So Q, because I don't know I'm at equilibrium, my Q expression is going to be products over reactants, just like my K. Product is HCl. That 2 in front becomes my exponent on the bottom. We have our 2 reactants multiplied, no adding here. Let's plug in our numbers and see what kind of value we get. 0.2 squared divided by 0.4 times 0.4, and what kind of value do we get? 0.2 squared divided by 0.4 times 0.4. 2.25 for my Q. Well, my goodness, look at that. When we compare Q to KEQ, so our Q was 2.5 and our KEQ is 0.8, my Q is way too big. So that means no, I am not at equilibrium. My concentrations will continue to change until I reach that balance point. But which direction am I going to go? Am I going to make more products, or do I need to make more reactants? Go forwards or backwards? Since I want a decimal, I want more reactants. Here we have a number greater than 1, which means this product value up here is too big. So we need to shift away from products. We need our reaction to go backwards, to make more reactants, to make this bottom number bigger, so we can move towards this less than 1 KEQ. So we need our reaction to shift towards reactants. We need our reaction to go this way before we will hit that equilibrium point of 0.08. We need to shift quite a bit because that's greater than 1, that is less than 1. So again, the only difference between Q and KEQ is this is at equilibrium, the balance point. No more concentration changes. Our net concentrations remain the same. Q can be anywhere. As we showed here, this Q value tells me that I am not at equilibrium. My concentrations will continue to change, and it even can tell me how those concentrations are going to change. My concentration of reactants must go up, and my concentration of products must go down in order to get our reaction to this balance point. In our next video, we'll talk about Le Chatelier's principle and how I can actually force my reaction towards the products or towards the reactants instead of just letting it do its own thing. All these calculations here, we're assuming that the reaction is going to do what nature intended for the reaction to do. I'm not forcing it one direction or the other. But in Le Chatelier's, we can actually make it do stuff.